We can actually reproduce scenarios that you would see in an isolated microgrid in this lab. So yeah, we can go up to 500 kilowatts. People can bring in their equipment and we can test it here to see how it actually performs. We can also do straight up research here. We can run tests. So some things, Dave told you about some of the equipment we tested, but we've also run through different scenarios to show, for example, we tested how does ramp rates affect the fuel efficiency of a diesel generator. That was one recent test we did. So it's, you know, when you add a lot of renewables to the grid, your generator does a lot more ramping up and down to balance out the wind power or whatever it is you're putting in. And so we wanted to know there wasn't any public information about how that affects the diesel fuel efficiency. So we can test equipment, we can do research and training as well. So what we're going to do is we're going to run through a scenario today where we're going to pretend that we are a small isolated village in Alaska, 150, 200 people. Yeah, we're going to start out where a lot of villages are nowadays with just the diesel generator running. Dave is going to turn on the diesel generator. So this is we'll be looking at these screens here, and these screens are going to tell us what's happening in our microgrid. All right. On this screen here, we're going to see the power of our different devices. So right now we have plotted the blue line is going to be our load. So this is going to be what us, the consumers, are using as electricity. So our lights, our laptops, our TVs, whatever you use for electricity. And the red line is going to be the generator output. And so the two, at first they're just going to be, the generator is just going to match the load, because that's what happens, right? When things are working correctly. So now the generator's started up. This is the one-line diagram of the lab here. And so you can see each box represents a different component in the lab. And then remember, these are the circuit breakers. And so you can see that Dave just closed the circuit breaker. So he just energized our main bus with the diesel generator. And so everything that is red is energized, everything that is green is not energized. So our generator is energized and our bus is energized. So this box represents our generator. This is our wind turbine emulator, all right? This is just the meter. If you go over here, this is our load bank right now. So we have a load. We're going to emulate our electrical loads with a load bank. So that's what we just saw outside, those big boxes. Those are our electrical loads, and that's how we can reproduce the loads of our village. So we get data from different villages, and we get a time series profile of their electrical load over a year, and we can plug that in. We can plug in, you know, an hour or two or minutes of that profile into our load bank here and reproduce the same scenarios that you would see from that microgrid. This is our PV emulator. So this is that box you saw right over there that reproduces solar panels. And this is our inverter, the big ABB inverter that you saw. And then this is our battery management system. So this is for the large lead acid battery bank. All right. So right now our generator is running. We have zero load online. So we can run scripts in here, and we can program scripts and have very precise setup tests, or we can just manually put in numbers and make it run that way. So for the sake of a demonstration, we're just going to manually type in numbers and watch what happens, right? So let's put a load on the grid. So since we're a community of a couple hundred people, so our load varies between goes between 50 and 100 kilowatts. And so you can see right now, so Tana just put 50 kilowatts of load on. And so our generator and our load they both jumped up. But one thing to know about this display is that they operate on different y-axes. And so you kind of have to read the number here to see what the actual power output is. And so each line is scaled on its own y-axis. So it can be a little bit confusing. So sometimes it might look, oh no, how come the load is higher than the generator output? Well, it just got scaled differently. So I'll try to guide us through that. But you can see relative to over time, like how each line changes as you run through different scenarios. This spot here, this shows our grid frequency. Right, so normally you want to hold your frequency at 60 hertz. And so right now, but you know, there is a little bit of variability. So right now it's varying between, sure, max and maybe. Right now it's kind of going between 60.011 and 60.028. So it's holding a pretty tight window, which you would expect because the load's not doing anything. But since we're in a small microgrid, right? So it's a small system. There's only a couple hundred people, and so there's a lot of variability in our load. So load ramps up and down a lot, just over a short time scale. Because you know, when someone turns on a 1 kilowatt water, like a hot pot or whatever, like a water boiler, you see that in your whole load system. So there's not a whole lot of averaging in your system to balance out the load. So there's a lot of short time scale variability, and that affects your grid frequency. So you can see Tana just bumped up our load from 50 to 100. There we go. So you can see our load just bumped up, down and up again. And so you can see our grid frequency kind of responds. So when you have a step increase in the load, your frequency goes down, right? Because your generator is a spinning machine, and when you put a load on, and when you increase the resistance to that spinning, when you put a load on the machine, it slows it down until it's able to respond by putting more fuel into the engine and increasing its power to speed it up again. So that's why you see this drop in the frequency, and then when you do the reverse, you remove load from the system, you get a little bump in the frequency. But so there's a lot of inertia in the generator, which is a good thing, right? Because that gives you power, that stored energy that's stored in the spinning generator, that it releases when there's a change in the load, and it can absorb that change. But then it also slows down its response and bring it back to frequency. So it's just kind of like a slow responding system, but it always keeps it at around 60 hertz when it's in normal, good operation. So we have the short-term variability, then we have a diurnal variability. So at nighttime, our load is going to go down all the way down to 50, and then during the day, it'll go up to 100, and just kind of cycles back and forth like that. And then there's a seasonal variability as well. So we don't have any fish processing plants in this village. So our loads in the summer are going to be lower, and in the winter they're going to go higher. So there is a seasonal variability in our loads. So typically, unless there's commercial operations in the summertime, the winter loads are going to be higher, much higher, and the summer loads are going to be much lower. We decide, well, let's put some wind power in our system so we can reduce how much fuel we're using, right? All right, and we buy a 50 kilowatt wind turbine. And we install it on our grid. We commission it, install it, and so let's fire up. So Tana's going to now start our wind turbine emulator, and so it'll be noisy. So right now you hear it spinning up, and there will be some loud chirps as it synchronizes with the grid. So right now it's synchronizing. Remember we talked about synchronizing. So it's synchronizing with the grid. Speeding up. All right. So we just synchronized the wind turbine with the grid. So now our wind turbine is running online. This yellow line, this is our wind turbine power. So we just put, so now wind turbine is outputting 10 kilowatts, right? It's a 50 kilowatt wind turbine, but it's not going to always put out 50 kilowatts. It depends on what the wind is. And so the wind power is going to vary up and down. You know, especially for these small wind turbines, there's not a lot of control you have over its output. Some of the larger wind turbines that are being installed now in different places, they have pretty nice control. They can limit their output, so it will stay below a certain value. But if we're just installing a small 50 kilowatt wind turbine, it's going to follow whatever the wind's doing. There's some control maybe, but pretty much your generator has to take up the slack. So our generator is making up the difference between our wind output and the load. Alright, so remember the red, this is our generator output, and the yellow is our wind output, and the blue is our load. So you can see the generator is basically just balancing out whatever the wind's doing. And you can see also on our one line, our wind power is also, not there. Let's look at the frequency. Look at what our frequency is doing now. So you can see our frequency is spiking up, spiking down, and that corresponds to ramp increases and decreases in the wind power. We have, you know, the frequency. There's a little more variability in our system frequency. It's not great, but we're saving fuel, so it's good, right? And so right now, our frequency is going between 59.982 and 60.041. So it's not bad. It's still not bad. One of the reasons for that is we're running a pretty large diesel generator right now. And so these are all pretty small load steps for it. So if we're running a smaller generator, change in the frequency would be larger. So remember, our system load, you know, it kind of goes between 150, and we've had 50 kilowatts of wind power installed. So we don't have to curtail wind that often. Sometimes if it's a windy night and our load goes down to around 50, we have to curtail some of our wind power because we need to keep the generator online. We can't turn our generator off yet, right? There will be 50 kilowatts of wind power. What's going to happen? The power is going to try to go into your generator. The generator doesn't like that. It's going to trip off right away. We've done that in this lab, and it does that. That's what happens. And so what happens when your generator trips offline? All of a sudden, you have no more grid, and so the wind turbine is going to trip offline, right? And then you have nothing. So then you have a blackout, and then you have to start everything up, figure out what happened. Okay, start it up. So no one likes blackouts, and they take, you know, they're hard to start your grid up again. So we need to, and that's where the minimum loading comes in as well. So usually, let's say we want to keep 30% on our generator. So that means we need to curtail our wind power. That means if we're able to produce 50 kilowatts of wind, we have to rein it back so that we're only producing 30 kilowatts of wind power, right? And so there's different ways you can do that. A lot of places they'll have a dump load. So they have a resistive load where they are taking the extra wind power and they're just they're making heat with it. Sometimes that heat is wasted. A lot of times you use it as it's like have a water boiler. So you're heating up water. And this is connected to some small district heating loop where you're providing heat to your power plant, your community center, school, laundromat, that sort of thing. You do a good job designing your system, it doesn't go to waste, right? But electricity is more expensive, so you use electricity for electricity when possible, and then when you have too much, you use the rest for heat. But we only have, it's not that big of a wind turbine, so we're not spilling that much wind power. So we're actually displacing quite a bit of our diesel fuel, which is good. We're really happy with how this wind turbine is working. So what do? We buy another one, right? Now we have 100 kilowatts of wind power. So now what happens? Now Ton is increasing our wind power. So we buy it, we install another one. Now we got two of these things. both working. So our yellow line, this is our wind power. The wind power is increasing. What's happening to our red line, our generator? It's decreasing. So the loading on our generator is going down. So now what's going to happen? We're spending a lot more time with the low loading on our diesel generator. We keep the same generator running. We can't turn the generator off, right? We can't turn the generator off for the same reasons. Because if the wind power drops down to 0, we need to have that generator there. So we keep the same size generator running. What that means, we're low loading our generator. When you low load your generator, it's less, the efficiency is lower. You don't get as good of fuel efficiency from your generator. The generator also has a harder time maintaining your system frequency. So your power quality isn't as good anymore. Also, now we have 100 kilowatts of installed wind power on our grid, where our maximum load is about 100 kilowatts. So what's going to happen? We're going to curtail a lot more wind, right? We have to rein back that wind because we can't let it go. We can't let it get close to low loading our diesel. We have to keep 30% on our diesel. So we're using a lot more of our wind power as heat, or worst case scenario, we're just dumping it. We're just not using it. So from the second turbine we installed, we're still saving fuel. We're still saving fuel, but we're not saving as much as we saved from our first wind turbine. Right? So we're still happy with it, but we're not. The savings aren't as much as our first. So there's a decreasing savings as you increase the amount of wind power you put on your system. So let's just run this scenario. Let's say, how much wind do we got right now? 30 wind. So what happens if we drop that down to 0? So the wind's going, all of a sudden it trips. The wind goes down to 0. The generator picks it up. You couldn't really tell. There wasn't really any noticeable difference, right, to the load. You couldn't even hear a difference in the generator. It's a pretty big generator. But so as a customer, this is what you want. You don't want there to be a noticeable difference in your supply of electricity. You don't want to pay too much money for fuel, right? And you want there to be electricity. So and this is a service that the generator provides. When there's a drop and that wind power goes down to 0, the generator just picks up that load like nothing happened, and you still have electricity. You pay for that by buying fuel, right? So there's a cost to that. That's the service it provides, and it does a great job. We can ramp this wind power up and down as much as you want, and the generator is just going to make up the difference. So it's a great tool. So now we have a lot of wind power in the system, and we decide, all right, well, it seems like everyone's getting batteries nowadays, right? So maybe we should get a battery. This is going to help us use more of our wind power. Smaller systems like this, there's starting to be a lot more options out there for grid forming inverters and battery systems. Let's put the battery on our. Let's turn the battery on. We're starting it up. Right. So it will be loud. So there's going to be 2 loud bangs. Nothing bad is happening. So basically there's 2 circuit breakers that have to close to energize our battery system. There's the first one is going to close on the DC bus and connect our DC bus to our inverter. The second one is going to close the inverter onto the AC bus. So the second one to close needs to synchronize first, right? So everything needs to synchronize with the grid. But they're working on something like that. Alright, so that's the first bang. So you can see that we closed the battery system to the inverter. Now the inverter is closed to the grid. So the different colors on our one line represent whether it's a load or a source. Okay. So red means it's a source of power, and blue means it's consuming power. So right now our inverter is consuming power, and our load is consuming power. So this purple line is our inverter right here. So it's just consuming a few kilowatts. Basically, so we're running our inverter in troop, which basically means we try to get it close. It should be roughly close to zero at 60 hertz, and then it will respond to changes in the frequency. So when there's a spike in frequency, it's going to absorb power, and when there's a drop in frequency, it's going to pull power out. Because remember, when we looked at our frequency plot, when we increase the load, when there's a step up in the load, the frequency goes down, right? So when the frequency goes down, that means there's not enough power. And so our battery is going to help out the generator by putting power into the grid. And when frequency goes up, that means there's too much power. And so our battery or inverter is going to help out the generator by absorbing power. But for a normal operation, it's just going to sit at zero. So this is why I talked about, it's a little bit confusing sometimes because they all have their own scaling, right? And so you can't necessarily compare the lines with each other in terms of their magnitude. So what the generator is doing, the generator is making up the difference between the load and the wind power. And so what's our wind power right now? And our load is 100. So let's increase our load up to 20. Or not load, sorry, wind power, yeah, my bad. Right, so we just increased our wind power, there's our yellow. Our generator output went down, and the load stayed the same. Look what happened to our inverter output. It dipped down. If you look at our frequency plot, it was hard to see. You didn't quite catch the resolution there. Maybe let's do another. Maybe let's drop the wind power down to zero. Right. So we dropped the wind power down to zero. Right. See what happened to our frequency? The frequency dropped. There was a dip in the frequency. Look what happened to our battery. Our battery output shot up. Right. Because when the frequency drops, that means there's not enough power in the grid. This red line is our generator output. So you look at the response of the generator. So it gradually responds like that to respond to the change in the amount of power, and the battery responds immediately. And so they can kind of help each other out like that. So the battery immediately puts this power into the grid to supply the difference, and then the generator responds slightly slower. And so right now, the battery is helping improve our power quality, right? Because our power quality wasn't as good because we added all that wind power to the grid. And so the wind power is ramping the system up and down, and the generator is having a harder time maintaining our frequency within acceptable bounds. Now we put this inverter and battery on the grid, and it's helping. It can help the generator to maintain our system frequency, which is great, right? But what do we actually care about? As a consumer, we're not thinking about what's the grid frequency. We're thinking about how much money are we paying for this? How much money are we paying for fuel? So how can we save fuel with our battery? So far we've been having to run the same size generator all the time. It doesn't matter how much wind power we put on the grid. We've been running the same size generator. The generator, as long as it's running, is consuming fuel, and the generator has to keep a certain loading on it. And so, in order to save fuel, you want to run a smaller generator, or you want to turn that generator off. Now, the reason why we couldn't put a smaller generator before, or turn the generator off. Well, the reason why we couldn't put a smaller generator before is because if the wind power, if there's a drop in the wind power, you need something there that's able to output that power. So you had to have a generator that's big enough to cover the whole load in case the wind power drops to zero. So this inverter is what people call a grid forming inverter. So like Dave said, it's a very powerful inverter. That inverter we have over there is able to form the grid. So remember how we said the generator, it makes that frequency, sets the grid voltage and frequency that everything else follows. This inverter can do that. So this inverter is can supply a lot of the same services that the generator supplies, but it doesn't consume fuel while it does that. It takes energy that's stored in the battery. That's a great way to save fuel. There's a few communities that are actually able to do that for parts of the year, and there's a few that are working on right now that are installing systems that will let them run off of their inverter and turn their diesel generators off. And the projected savings are quite large for being able to do that. So it's a really exciting time, and like we said, the performance of these inverters are going up and the costs are going down, and so they're just starting to become economic to run in these sorts of in certain situations. So exciting times. So what do you think would happen if we turn the diesel generator off now? Let's have a vote. We have the inverter's going to form the grid and blackout. Who thinks blackout? Who thinks inverter formed the grid? All right. We're going to put money on the table. We're going to reduce the load on our diesel generator because you don't want to open a circuit breaker where there's a lot of current flowing through it, right? So we're going to slowly reduce the load that our diesel generator is supplying, and then we're going to open up the circuit breaker and see what happens. So you can see the red line here, this is our diesel generator. So now we have 19.5 kilowatts on our generator. And so Dave, our power plant operator, is going to open up the circuit breaker. What just happened? Red zero. Our generator is not doing anything right now. What happens to the purple line? Purple line shot up, right? What's the purple? Purple is our battery, our inverter. So what just happened? Our inverter is forming the grid. We still have our wind power on, right? The wind power is still outputting. We wouldn't be able to do it without the inverter online. So basically, this inverter is providing the same services that the diesel generator is providing. It's forming the grid. And so now if our wind power goes up and down, the inverter just does the same thing that the generator was doing. It balances out the difference between the wind power and the wind power and the load. One difference between the inverter and the generator is that, remember the generator, you couldn't get close to putting zero load on the generator. You couldn't let the wind power get close to the load, supplying all the load, because then you're in the danger zone, right? You're getting awfully close to reverse powering your generator, and you also don't want to put too low of a load on your generator. Well, our inverter doesn't matter, it doesn't care. They can take power and you can put power out. So we can let the wind power go higher than the load. And the inverter will just go positive power output, negative power output. And it'll just balance out whatever's happening between the wind power and the load. And so if we increase the wind, so now look, our inverter is going negative power, so it's charging, right? Because we have more power, more wind power than we have load. And if the wind power drops down, it goes positive again. Pretty cool. It's very smooth. So as customers, right, all of us are customers, consumers in this grid. We all get electricity that are powering the loads. We have no idea that they just turned the generator off. We couldn't tell the difference. We can't tell the difference between the electricity from the generator or from the inverter or from the wind power. That's what you want, right? The inverter is, fulfilling the role of the generator and consumers downstream didn't notice any difference. And that's kind of, yeah, that's good. That means you had successful installation. And there's enough wind power you can run with just your inverter and how much energy you have stored in your battery. Your energy in your battery goes too low, your wind power drops down, bring the generator back online, and the generator does what it's good at. Oh, you have wind power, bring it back off and run with your battery.